Assalamualaikum warahmatullahi wabarakatuh. Selamat siang teman-teman semua.
Selamat siang, Pak.
Ya, Mbak Putri, teman-temannya diminta untuk segera join ya, Mbak. Karena nanti jam 2 insya Allah Prof. Nisan akan bergabung untuk mengampu kelas OPB hari ini.
Baik, Pak.
Menariknya dulu tuh memang 3, sekarang itu nggak jadi 1. Nah, jadi dulu Gunung Rakata, Gunung Dawan Danan sama Gunung Perbuawatan itu terbentuk dari satu dapur magma yang sama, Wak. Jadi walaupun memang kelihatannya ada 3
Untuk teman-teman semua diharapkan nanti aktif ya, kalau bisa ketika Prof. Nisan membuka sesi tanya jawab, teman-teman menyampaikan pertanyaan seperti itu. Nah, di sini akan saya pantau, saya mengikuti kelas ini, dan bagi yang aktif nanti akan saya catat sebagai nilai tambahan.
recording.
Good afternoon, Prof. Nisan.
Good afternoon. Can you hear me?
Yes, I can. It's great to see you again.
Yeah, good to
How
see
are
you.
you?
Pretty good. You?
Okay, I'm good. I think the student ready to receive your lesson from you.
Yeah, okay, sure.
Okay, good
So,
afternoon, everyone. Very fortunate this afternoon, Prof. Nisan has joined us. He will present the multi-state separation material. Okay, Prof. Nisan, this time is yours.
right, sure. Hello, good afternoon. So let me share my screen. Oh, okay. I just sent a request for sharing screen. I think that was not enabled.
Tolong Mbak Putri dibuat bisa untuk sharing screen ya, Mbak.
Baik, sudah Bapak.
Oke, Prof.
Yeah, okay. I think it's fine now. Okay, can you see my screen now?
Yes.
All right, great. So let's get started.
Yes.
Great. So what we actually discussed in our face-to-face session was today we will be designing the distillation column, or we get started with distillation column, right? So in the last class, we just finalized some of the terminologies. So in a distillation column, you have a feed, and that feed you wanted to purify. So what it means is at the end, what we want to do is we want to get the light things at the top as distillate, and we want to get the heavy things at the bottom. Agree? And the way we do is we provide heating at the bottom through the reboiler. So the things that cannot really stay as liquid form vapor, go to the next stage. Then when it reaches the next stage, the temperature will be lower. So part of it condenses, but the things that are lighter, it still remain in the form of vapor, which go to the next stage. where the temperature is even lower. Then whatever remains as vapor further go up. So by the time it reaches the final stage, it's at the least temperature. So only the lightest things can stay in the form of vapor at that time. So that vapor goes to a condenser and it completely condensed into the product. Now, once it's completely condensed, part of it we collect as the distillate and part of it is sent back to the column as reflex. So in the last class, we also discussed that one of the reasons for using the reflex is this reflex is the purest component. So it gets mixed on the stages below. And here, the purity is not as good as the final product. So when we add reflex into that, it improves the purity, right? So the number of stages that's necessary to bring
Oh, namanya nih Rizhan,
the desired composition would get lower. So by having a high reflex, we can get the desired separation using less number of stages. So this is what we pretty much discussed in the last class. Of course, we also talked about some of the fundamental topics such as how do we estimate the bubble point and how do we get the dew point and things like that. So before we continue into the new topics today, is there any question? So if there is any question, you can either ask now or you can just put it in the chat. Right. All right, so looks like everything cool. So in that case, I'm continuing. Now, as I mentioned in the last class, the way we define reflexes, the flow rate we are sending back to the column over the flow rate of the product. So if we send more back into the column, the reflex definitely is higher. So if reflex is higher, we can achieve the desired separation with less number of stages. At the same time, the size of the condenser will get bigger. We need a lot of energy for forming the vapor. So that means our operating cost increase. So it's not really possible to say what actually is the best combination of reflex and number of stages. Because if the reflex is high, we can reduce the number of stages, but at the same time, the operating cost can be much higher. Now, in a distillation column design scenario, there are certain specifications, which means we typically know what goes into the column. And we typically know what flow rate we are getting. Now, typically, we also know at what condition the feed is coming. And we can also set the pressure of the column. So these things are typically known when we start. So what we actually try to do during the design stages, we need to estimate what actually is the minimum number of stages or what's the limit of the number of stages desired for separation. Similarly, what's the minimum reflex ratio needed to get the desired separation? Now, once you get the minimum number for the number of stages and reflex, then the next stage is to identify what's the real number, because minimum number of stages we get only if we use total reflex, whereas minimum reflex ratio is when we have a large number of stages, or we can also call an infinite number of stages. So only in that situation, we get the separation done with minimum reflex. So here, what we are trying to do is an actual combination of number of stages and the reflex. And also we need to see where we need to put the feed. So these are the design targets. So based on the specifications that we have, we need to identify these numbers. Okay. Is there any question? Right. So in that case, the first thing we need to do is we need to estimate the column condition. So in the last class, we did talk about the bubble point and dew point. So what can we say about the bubble point and dew point related to the column condition? So anybody wants to give a suggestion or feedback on that? How would you do? How would you use the bubble point and dew point to estimate the column condition? So here is the column. So in this column, when something reaches the condenser, it's coming in the form of vapor. So if it's coming in the form of vapor, suppose this vapor temperature, what can we say about this vapor temperature? Remember, this is a mixture with many components. So what can we say about the temperature of this vapor? Is there any response? So what can we say about the temperature of the vapor? So you can type what do you think about that? So the question is, you have your final product in the form of vapor that reaches the condenser. So what could be the temperature of that vapor? So can that be bubble point or dew point, anything like that? So remember, the top of the distillation column is our product. Agree? You have a certain things in the feed, and those things we send to the column. The heavy things go to the bottom, light things go to the top. So eventually when it reaches the top, we have the target composition for the distillate. Now, those things enter the condenser in the form of vapor. So only after the condenser, it gets condensed and product is collected. So when it enters the condenser as vapor, what could be the temperature of that vapor? So how do we estimate the temperature of vapor? Based on what kind of calculation? No response. Right, so that will be, since it's vapor, now we need to keep this in mind. So this vapor has a certain composition and a certain temperature. If that temperature is above the dew point, what will happen is like some of the things here, some of the heavy things here, that also get vaporized, which means this composition will not be the composition of the distillate. Whereas if the temperature here is lower than the dew point, some of the lighter things we wanted as a product that get condensed. Because if the temperature is lower than dew point, more things will go from the vapor into the liquid. So in order to get something at exactly the same composition, the vapor that's leaving here should be leaving at the dew point. Similarly, the bottom, we have certain products here. So we have certain materials here. And if the temperature is above the bubble point, some of the heavy things will also go into vapor. So we won't get it at the bottom. Similarly, if the temperature here is lower than the bubble point, some of the light things, they also get condensed because they won't stay in the form of vapor. So that will go with the bottom. So in order for the bottom to go at a specific composition, the bottom must be at the bubble point. So in a distillation column, we typically know what we want to get at the distillate. The distillate composition, we need to know because that's our target. The purpose of doing this distillation is from the feed, we wanted to get a few things in the form of the distillate at a certain composition. So because of that, we know the distillate composition, and we also know the bottom composition. Since this composition is fixed and this composition is fixed, we can estimate the temperature of the top by performing a dew point calculation, and the temperature of the bottom we can estimate by performing a bubble point calculation. So based on the distillate composition, we perform a dew point calculation so that we get the top temperature. Based on the bottom composition, we perform a bubble point calculation to get the bottom temperature. Right. So any questions so far? All right, looks like no question. Now, as I mentioned earlier, the way we perform a distillation column calculation is we need to estimate the number of stages and also the reflex we wanted to use. But before we perform those calculations, the first thing we need to know is what are the limits. So that means what's the minimum number of stages that we need? Similarly, what's the minimum reflex we wanted to use? But we need to keep in mind, in order to get the separation done with minimum number of stages, that means the reflex must be maximum, because as we increase the reflex, the number of stage required will be lower. And eventually, the absolute minimum number of stages would be the reflex is complete. That means we don't collect any product. We send the feed, we heat it, the product form at the top, but instead of collecting anything, we just send it back to the column. So only at that condition, we can achieve the separation with minimum number of stages. So the minimum number of stages means the reflex is maximum. And at this stage, the separation can be achieved with minimum number of stages. But at the same time, this kind of operation is not really practical. And the only time we, in the real industries, we perform a distillation under total reflex when we try to get the plant into the steady state mode. So once the plant reaches the steady state mode, we shouldn't run the column at total reflex, because total reflex means the feed is going in, but we are not collecting anything. So we just distill so that the purity would be reached with minimum number of stages. But then, since we are not collecting anything, that distillation is practically meaningless. Agree? So the reason that we still estimate the minimum number of stages, that will give us a limit. So below that number, we cannot get the separation done, no matter how big the reflex we are using. So remember, here we have a feed going in, but nothing is coming out, which means if we do the distillation with minimum number of stages, what it means is the size of the condenser has to be infinitely big, and the size of the reboiler also must be infinitely big. That's because something is going in, but nothing is coming out. So that means everything that's going in, it has to be accumulated within the condenser and within the reboiler. So, and also within the column. So because of that, the column gets infinitely large, the reboiler get infinitely large, and condenser also get infinitely large. So this is not really for doing a practical distillation column. The only purpose we are estimating the minimum number of stages is because we want to get a theoretical limit. What's the absolute minimum number for us to get the separation done? Now, in order to get the minimum number of stages, we use an equation called Fensky equation. Now, once we identify the minimum reflex, the next is to identify a limit on the minimum reflex. So minimum reflex is when we use a large number of stages, which we can call an infinite number of stages. So if the number of stages is more, the reflex needed is lower. So as we keep increasing the number of stages, the reflex requirement get minimum. And we see that after a certain number of stages, the reflex is not really changing much. So the theoretical limit on the minimum reflex in order to get a desired separation is called the minimum reflex ratio. Now, to find the minimum reflex ratio, we use an equation called Underwood equation. So try to imagine what will happen if we operate a column with minimum reflex. So when we use minimum reflex, the condenser size would be small because the reflex is minimum, and the reboiler size also is small, again, because we need to condense minimum vapor. But the problem is the number of stages become infinite. Because of that, the cost of the column is also infinite. The other way to say that is, if you run a column at minimum reflex, our column would be infinitely tall, but the diameter would be smaller. Whereas if we run this column with minimum number of stages, the height of the column would be small, but the diameter would be infinitely large. So the design approach for a distillation column is, we initially find a theoretical limit on the minimum number of stages. Then in the next stage, we find a theoretical limit on the minimum reflex. Now, once you find these two, we know that we need to operate above minimum number of stages and above minimum reflex. But the question is, what actually is the combination? So for that, there are certain ways. So the first one, so to get started, we use Fensky equation to find minimum number of stages. And later, we use an equation called Underwood equation to find minimum reflex. Now, once you find a combination of these two, in the next step, what we do is we fix either the number of stages or the reflex. We shouldn't do both, or we cannot find both simultaneously because the number of stages and reflex are interdependent, because the number of stages and reflex depends on each other. So if we have more number of stages, we need less reflex. So because of that, in order to find a combination, we need to fix one. But when we fix one, we need to make sure that we are fixing that number above the minimum. For example, if you're fixing the number of stages, we need to make sure that the number of stages must be a number that's above the minimum number. Then we use something called Erbar-Maddox correlation to find the combination of the number of stages and reflex that give us the desired separation. So any questions before we start talking about the design procedure? No questions? By the way, if you have questions, either you can type it or you can ask it straight away. All right, silence means no questions. So I hope everything is clear so far. So what we do is we straight away start the design procedure. So in the design procedure, there are two types of problems we usually try to do. So one is we try to achieve a certain purity, because the purpose of distillation column is we wanted to produce certain chemicals at a desired purity. So that can be one of the targets. Whereas another kind of target could be a component recovery. So basically what it means is, suppose you have three components, A, B, and C. So let's say in the feed, you have 20 moles of A. Then let's put a number here. 65 moles of B. So it's how much? 85. And 15 moles of C. So suppose the purpose of doing this column is you want to produce this, pure A, which means that when you send this to a distillation column, you want A at the top. And here, in many cases, you might, the target may be you want A to be with a purity of 95%. So this is one kind of problem. So that means we want A at the top, but we want that with a purity of 95. So this is one kind of problem. Another kind of problem is from this mixture, you want to get a certain amount of A at the top. So for example, so let me write it down at the bottom. So suppose, so I'm not really talking about purity. All I'm saying is I want probably 18 moles of A at the distillate. So now you see the difference, right? Because in the first type of problem, we talk about purity, but we don't really talk how many moles of A comes to the top. So for example, out of 20 moles, we can just let 9.5 moles of A come to the top and 0.5 moles of B comes to the top and none of the C goes to the top. So in that case, you still have a purity of 95, right? So case A is case 1 is the distillate is 9.5 moles of A and 0.5 moles of B. So this is one case. In case 2, we only talk in terms of recovery. So that means, let's say 18 moles of A goes to the top. But we don't really say what purity that we want. So when 18 moles of A goes to the top, perhaps 7 moles of B also goes to the top. Maybe 5 moles of C also goes to the top. So in the case 1, out of 20 moles of A in the feed, you only have 9.5 moles of A at the top. Of course, whatever A at the top, you get with a purity of 95% purity. So this target is met. Whereas in the second case, out of 20 moles of A, you manage to get 18 moles of A at the top. So the target is met. But the problem is, in the second case, at the top, overall we have 30 moles, which means the purity here is, so 18 over 30 is just 60%, right? So in a distillation column design, we can do the design in any of these fashion. So now my question is, case 1 or case 2, which one looks more reasonable or realistic? What kind of case we typically do, or what actually should be the case or the targets we should be setting in a distillation column design? So either case 1 or case 2, which one is more having more practical application? What do you think? You can even just type your response without really giving an explanation. So it could be just case A or case B, depends on what you feel. So in case, so you can do another thing if you don't want to type. I actually typed 2 cases, case 1 and case 2. So you can just give a reaction like a like or thumbs up. Case 2, great. So one response is case 2. Another thing you can actually do is I type 2 cases, case 2. So 2 people believe it's case 2. So how about others? So in case you don't want to type, you can just give a thumbs up, just like this. So if you think it's case 1, you can just put a thumbs up near case 1. If you think it's case 2, you can put a thumbs up near case 2. Or you can just type. Either way is fine. Case 2. Right. Great. So more people actually believe it's case 2. All right. But now, if you look into this, if it's case 2, we can get most of the A at the top. But let's say this is the final product. So suppose you are in the company that produce this product A. So even though you can get most of the A at the top, the purity is quite poor. But if the customer wants 90% purity, then you cannot sell this. At the same time, if you go by case A, you are meeting the purity requirement, but you're losing a lot of your product. So the whole point is, we cannot really say that case 1 is superior to case 2 or case 2 is superior to case 1. It really depends, but in most of the cases, we need to fulfill both case 1 and case 2. That means we need to recover a high amount of A, and we need to recover A with a high purity. So that means when you recover a high amount of A, it's case 2. We need that. And whatever A we are getting, we might also need that with high purity. So high recovery and high purity. So when we meet these two targets together, yes, that's when we actually have the best design. Okay. So of course, in most of the cases, it may be quite difficult to target both. So it also depends at what stage we are designing the column. So if your distillation column is in the intermediate stage, probably case 2 is more important. That means we need to recover more. But if you are designing the last column, then the purity is also quite important, because the customer won't accept your product if the purity is not met. Okay. Now, when you are designing a binary distillation column, the composition targets are fairly easy to set. It's easy to set is because you only have, for example, instead of 3, you only have 2 products, A and B. Let's say the original feed is 60 moles of A and 40 moles of B. The reason that this is easier to set is because if, let's say, you try to get 55 moles of A at the top, right? And you want to limit the amount of B at the top to 5 moles. In that case, we can automatically say what you get at the bottom, because whatever not at the top, it should be at the bottom, right? So out of 60 moles of A, if 55 goes to the top, 5 moles of A should be at the bottom. Similarly, if 5 moles of B goes to the top, then 35 moles of B at the bottom. But when you have more than 2 components, it's really hard to predict how the components will be distributed between top and bottom. That's because you can always control 2 components, because distillation column has just 2 outlets. So you can say how much of one of the components go to the top and the other component go to the bottom. But your feed might be 6 or 7 different components. So in that case, it's fairly difficult to predict how much of each component goes to the top. So because of that, we use the concept of key components to get an initial estimate on how the components will be distributed in the distillation column. So the key component, the concept is like this. So suppose you have a mixture and you wanted to separate those into distillate and bottom. So let's say in the mixture, you have 5 components. So let's say you have A, B, C, D, and E. So let's say they are boiling points. So here I write the boiling point in degrees Celsius. Okay. So for A, let's say this is 110. For B, let's say it's 130. C maybe 165. And D maybe 180. And E maybe 210. So in this case, suppose the purpose of this distillation column is to get most of the B at the top. So that means these two components at the top and the remaining three components at the bottom. So suppose this is the target in our distillation column. So we have 5 components, A, B, C, D, and E, and we have seen the boiling points here. So A has the least boiling point, E has the maximum boiling point. Now, what I want is, I want A and B at the top, C, D, and E at the bottom. Now, here is the question. So I want A and B at the top. So if I try to keep A and B at the top, what's more difficult to keep at the top? It's A or B. And what's the reason? So my question is, I have 2 components I wanted to keep at the top, A and B. Now, out of these 2 components, which one is harder to keep at the top? Is it hard to keep A at the top or it's hard to keep B at the top? What do you think? So
Be
it's
the top, Prof.
B at the top is hard. Reason?
Because the temperature is higher than A. And
Yes,
near
exactly. So here what happens is A's boiling point is 110, whereas B's boiling point is 130, which means if you try to keep B at the top, since B is heavier than A, there would be more tendency for B to go to the bottom. Now, if you apply the same logic here, it's harder to keep C at the bottom because C is the lightest. So if you can keep most of the C at the bottom, naturally D will remain at the bottom and E also will remain at the bottom because D and E are heavier than C. So because of this, when we design a distillation column, these are the 2 things we needed to control. So B is the hardest to control to go to the bottom, and C is the hardest to control to go to the top. So because of that, these 2 components are called the key components. Now, there are 2 key components. One is B and the other one is C. So for B, we call it a light key. So the reason we call it light key is because it's the light component among the 2 keys. Similarly, C is called the heavy key. Okay. Now, anything lighter than light key, we call it light node key. And anything heavier than heavy key is the heavy node key. So the concept here is light key is the hardest to control, and light key and heavy key are the hardest to control. Okay. Now, once we identify the key components, which is based on our target, we make an assumption. The assumptions here is anything lighter than light key almost exclusively collected at the top, and anything heavier than heavy key is exclusively collected at the bottom. The reason that this assumption is reasonable is because light key is the hardest, but we are controlling how much of light key goes to the bottom. So because of that, we can assume that anything lighter than light key, which pretty much stays at the top. Similarly, we are controlling the lightest thing at the bottom from going to the top, which means anything heavier than that, it should be a lot easier to keep at the bottom. Now, there is also another way, which is not really recommended when we do the design. Suppose we keep D as the light key, and instead of C, suppose we take D as a heavy key. In that case, what will happen to C is, since C is lighter than D, but heavier than B, what will happen is some C goes to the top and some C goes to the bottom, which means C is not really collected either at the top or at the bottom, which means if you want to separate pure C later, we need to separate it from both top and bottom. So because of that, it's usually not recommended to have a component between light key and heavy key. But if we decide to do like this, then it's called an intermediate key. So what we do now is we do a really quick activity. So the activity is we have 5 components. Now here I have given the expected displayed and bottom composition. So the question is, based on this data, what's light key and what's heavy key, and what's light known key and what's heavy known key. So can you type your response in the chat box? So the questions are, in this mixture, what's light key, what's heavy key, and light known key, heavy known key. Maybe 1 minute, 2 minutes. Right, so based on this system, so we know what actually is in the field, right? 5 components. So based on these values, what components the designer is trying to keep at the top, and what components the designer is trying to keep at the bottom? So for example, propane, there is 4.46 in the feed, and all the 4.46 is at the top. Isobutane, 10.84 is in the feed, and out of that, 10.82 is in the distillate. And butane, 18.1 is in the feed, 17.68 at the top, 0.42 at the bottom. Isopentane, 11.65 in the feed, 0.8 at the distillate, 10.85 at the bottom. Pentane, out of 20.40, 20.39 at the bottom. So based on this, what can we see as the design targets? What are the components the designer is trying to keep at the top? And what are the components the designer is trying to keep at the bottom? What components the designer is trying to keep at the top? So based on this, what components the designer is trying to keep at the top? Looks like some answer. So light key is propane, heavy key is pentane. Light key, propane, heavy key, pentane. Any other answer? Well, light key, propane, and isobutane. Right. So here, see, there are three things the designer is trying to keep at the top, right? Because apparently, out of the five things, the designer's target is to keep propane, isobutane, and butane at the top. Because the amount of these things go to the bottom is either zero or minimal. Whereas isopentane, most of it's at the bottom, and pentane, again, most of it's at the bottom. So that means the designer is trying to keep isopentane and pentane at the bottom, propane and the two butanes at the top. So in that case, since the designer is trying to keep propane and two butanes at the top, which one is the hardest to keep at the top? Propane, isobutane, or butane? Which one is hardest? Light key is butane as a component that serves the boundary between the top and bottom. Heavy key is isopentane. Yes, exactly. Because here, out of the three things that are going to the top, butane is the hardest to control. So what the designer did was, he specified, yes, the target, of course, is to keep butane at the top, but since it's not practical to keep everything at the top, you allow a small amount of the butane to go to the bottom. So butane is the light key. Now isopentane, that's the hardest to keep at the bottom, because between isopentane and pentane, this one is the lightest. So this one is the hardest to keep at the top, to keep at the bottom. So we allow a small amount of isopentane to go to the top. So the when we try to design this distillation column, our target is to control the amount of butane that goes to the bottom and to control the amount of isopentane to go to the top. So because if you can control this, anything heavier than pentane would be easier to keep at the bottom. Similarly, if you control the amount of butane goes to the bottom, it should be easier to control propane and isobutane going to the bottom, which means if most of the butane is at the top, anything lighter than that would end up at the top. Make sense? Any questions? All good? Yeah, so the response written here is fairly accurate. The light key, butane is the component that serves the boundary between the top and bottom. Heavy key is isopentane, just below the butane in volatility. Exactly. Right. Now, in a distillation column design, the first target is to identify what's light key and heavy key. Now, once the key components are identified, the next step is we need to estimate what is the minimum number of stages that's necessary to get this separation done. So for that, we use this equation called Fensky equation. So Fensky equation is stated like this. So the minimum number of stages can be obtained from 4 mole fractions and 2 alpha values. So this equation can look a little complicated, but in a way, this is fairly easy to understand. So if you see this XLK in this equation, this XLK represents the mole fraction of light key at the distillate. Now XHK is the mole fraction of heavy key at the distillate. Then XHK B means mole fraction of heavy key at the bottom, and XLK at the bottom means mole fraction of light key at the bottom. Now here we have the ratio of relative volatilities. Now let's try to give a reason for this equation. So just imagine we are separating the light key and heavy key in a distillation column. Suppose we wanted to increase the mole fraction of light key in the distillate. Suppose we wanted to increase the mole fraction of light key in the distillate. Do we need more number of stages or less number of stages? Because light key, we wanted to increase, or the mole fraction should be high, which means we want to keep most of the light key at the top, which means we want to increase the purity. So if you want high purity, we need high number of stages or less number of stages. So XLK at the distillate, according to this equation, is the mole fraction of light key at the distillate, which means we want the distillate to be pure. If you want the distillate to be pure, we want more number of stages or less number of stages. Please type your answer. If you want more purity, we want high number of stages or low number of stages. High purity means high number of stages or low number of stages. Yeah, exactly, high number of stages. So if XLK is high, which means we need high number of stages. Now, if heavy key is at the distillate, that reduces the purity. So what we did was we kept this at the denominator, which means if a lot of heavy key also goes to the distillate, that reduces the purity of the distillate, which means we only need a less pure product. But if we need a less pure product, that means we only need to use less number of stages. Similarly, XHK at the bottom, that means mole fraction of heavy key at the bottom. If mole fraction of heavy key at the bottom means the bottom product has to be pure. If the bottom product has to be pure, that means we need a pure product at the bottom, which means we need more number of stages to achieve that. But XLK at the bottom means the mole fraction of light key at the bottom. If the mole fraction of light key at the bottom is high, what it means is some of the light key, which is supposed to be at the top, also goes to the bottom, which means we don't need high purity. We only need low purity. So if we need only low purity, we only need less number of stages. Now, if you want XLK to be high and XLK in the distillate to be high, XHK at the distillate to be small, that means this has to be high and this has to be small. In that case, the number of stages must be higher. Similarly, XHK at the bottom is high, XLK at the bottom is low. That means this also is high. So we'll be needing a huge number of stages. So that's the way we can actually reason out Fenske equation. Now, at the denominator, the alpha LK average means the relative volatility. So relative volatility is a measure of how lighter one of the components with respect to the other. So if light key's relative volatility is significantly higher than heavy key's relative volatility, that means the volatility between the key components is huge, which means we need less number of stages, because a high relative volatility indicates an easiness for separation. But if their relative volatilities are somewhat closer, that means we'll be needing a huge number of stages, because this is at the denominator. So in a way, the Fenske equation is more like common sense. You want high purity, more number of stages. If the alpha value is, or relative volatility is significantly different between the components, again, that will reduce the number of stages requirement. But if the relative volatilities are somewhat similar, then we need more number of stages to achieve the desired purity. Now, if you remember from the last class, the relative volatility means the ratio of K values, but K values change with temperature. So we can have one K value at the top, one K value on the first stage, another K value on the second stage. So similarly, different stages have different K values. And we cannot really predict the temperatures on individual stages. So what we do is we estimate the top temperature because we know the distillate composition. We estimate the bottom temperature because we know the bottom temperature, bottom composition. So we can do a bubble point calculation to find the bottom temperature. So when you estimate the bottom and top temperatures, we can also get the K values at top and bottom, just like how we did in the last class. So when we get the K values, we can get the alpha values. So when we get the alpha values at the top and bottom, what we can do is we take the geometric average so that we can find the average value for the relative volatility. Now, that relative volatility is used here. Now, when we take the relative volatility, it's recommended to use the heavy key component as the reference component. The reason we take the heavy key component as the reference component is because if heavy key component is the reference, then the alpha of heavy key, that become 1. Because an alpha of one component with respect to that component itself means 1. So this equation is will be slightly simpler to use because one term completely become 1. Agree. So just to make sure that we understand everything until this point, what we do is we do a simple example. So what I recommend you to do is maybe take about 3 minutes to read this problem and do the first part A. And if you can type your answer, or if you can share your screen to show what composition that you get. So you want to try that for a few minutes? So I'll let you read this problem first. So what this problem involves is you're given a certain feed and you have a couple of targets, because if you read this problem, you have N-butane, N-pentane, N-hexane, and N-heptane, 4 components. You also have the mole fraction of each component in the feed, and you are also given the total feed. So that means you know how much of each component is in the feed. So what you want is you want 90% of N-pentane in the distillate, and you want 90% of N-hexane at the bottom. So the first thing you need to do is identify the key components. Once you identify the key components, based on the specification, you can identify how much of these components are at the top and bottom. Agree? Now, earlier we made this assumption that anything lighter than light key goes to the top, anything heavier than heavy key goes to the bottom. So once you apply those conditions, you can predict exactly what goes to the top and exactly what goes to the bottom. So once you get the flow rates of the things that go to the top and go to the bottom, you can convert the flow rates into compositions, mole fractions. So can we do that? So once we finish part A, the second question is, based on that information, how do you find the top temperature and the bottom temperature? And then with that information, how do you find how many number of stages is needed if you use total reflex using this Pensky equation? So maybe you can take 2 minutes to read by yourself, and then we start solving this step by step. Right. So I believe the problem statement should be fairly clear. So based on this statement, what actually is our light key and what is our heavy key? Our key components based on the statement. So you can type your answer there. So what's heavy key, what's light key? Can somebody type it, please? Based on this problem statement, what's light key and what's heavy key? B is light key and C is heavy key. Perfect. N-pentane and hexane. Yes. N-pentane is the light key and hexane is the heavy key because that's what we are trying to control. Right. So if that's the case, how much of N-pentane is at the distillate and how much of N-hexane at the bottom? Can you calculate that and then type the answer here? So based on this specification, how much of N-pentane will be in the distillate and how much of N-hexane will be at the bottom? 90%. So 90% of the feed, right? So can you estimate that number? So how much N-pentane is in the feed? How much N-pentane is in the feed? You're right, it's 90%, but how much N-pentane is in the feed? See, the total feed flow rate is 100 kilomole per hour. And it's also given that of that feed, 40% is A, 25% is B, 20% is C, and 15% is D, right? So how much would be the moles of N-pentane in the feed? The total feed is 100 moles. So 25% of that is pentane. So how much pentane is in the feed? Exactly. So if total feed is 100, then N-pentane in the feed is 25 kilomole per hour. So out of that, we want 90% of N-pentane is in the distillate. So how much N-pentane will be in the distillate? So the feed is 100 kilomole per hour. So the amount of N-pentane, exactly. So amount of N-pentane in the feed is 25. And our target is 90% of that at the top, which means 22.5 should be at the top. So if that's the case, so that's about N-pentane. So if that's the case, how much of hexane will be at the bottom? So how much of hexane will be at the bottom? Well, the target is you want 90% of hexane at the bottom, right? So how much is 90% of hexane? I believe the 2 kilomole per hour of hexane, I believe you are referring to how much of that goes to the top, right? 90% of hexane in the bottom means 20 means 108. Yeah, 18 kilomole per hour, exactly. So if that's the case, so here you can actually see that 22.5 kilomole per hour of pentane goes to the top. But the feed has 25 kilomole per hour of N-pentane. If 22.5 goes to the top, the remaining should go to the bottom. Similarly, if 18 moles of hexane goes to the bottom, which means 2 moles go to the top. So if that's the case, how about butane and heptane? So what will happen to butane and heptane? So you're correct about hexane and pentane. So how about butane and heptane? See, you're saying that out of this 25 moles of pentane, 22.5 goes to the top. Remember, butane is lighter than pentane. So what will happen to butane? Where will that go? Top or bottom? So you have written here that 22.5 moles of pentane goes to the top. Butane means it's lighter than pentane, right? So where will that go? Top or bottom? Butane. Exactly. So all the butane end up going to the top. Naturally, all the heptane end up going to the bottom. So we can write the mass balance of this column in this manner. So you have this column that's kept at 405 kPa. So the feed is 100 kilomole per hour of feed. So it's given that 40% is A, 24% is B, right? 20 is C, and 15 is D. Now you have only two options. Either it goes to the distillate or to the bottom. So for the B, the specification is 90% goes to the top. So if 90% goes to the top, whatever left goes to the bottom. Then the specification for C is 90% goes to the bottom. So if 90% of C goes to the bottom, the remaining must go to the top. Now, since A is lighter than B, all A will go to the top. D is heavier than C, all the D will go to the bottom. So now we completely defined what goes to the top and what goes to the bottom. So we can estimate approximately what the distillate composition look like. So we need to design this column in such a way that we get this as the distillate composition, like this. We want this as the distillate composition, and we want this as the bottom composition. Now, once we have the distillate flow rates, how do you find the distillate composition? Now we have the flow rates of distillate and the flow rate of bottom. So based on this, how do you find the composition of distillate and bottom? So for example, what's the mole fraction of A at the distillate? Can you just tell that single one? What's the mole fraction of A at the distillate? So the amount of A at the distillate is 40, right? And the total distillate flow rate is 64.5. What's the mole fraction of A at the distillate? Either can you type the number or you can just type how to estimate that. See, we know 40 moles of A at the top, 22.5 B at the top, and 2 moles of C at the top. So when we add these three, we get the total distilled flow rate. Similarly, when we add everything that goes to the bottom, we got the bottom flow rate. So from there, how do we get the mole fraction? So to find the mole fraction, all we need to do is just divide the flow rate of each component with the total distillate composition, distillate flow rate at the distillate. And similarly, at the bottom, we just divide the flow rate of each component with the total bottom flow rate. Agree? So if you do that, then the mole fraction of A at the distillate would be 40 over 64.5, right? So that's why the mole fraction of A is at the distillate is obtained as 0.62. Similarly, we find the mole fraction of everything at the distillate. Here, we find the mole fraction of everything at the bottom. Okay, so that's the first part in this question. So any confusion about that? To find the composition of the distillate bottom, you need to use mole balance of each component along with the total flow rates of the, once the total flow rates of the distillate bottom, you can calculate the mole fraction of each component in both streams. Exactly. So that's what we did. Okay, good. Now that pretty much is the first part. So how about part B? So how do we do part B? So now the question is the top temperature of distillate and boiling point of bottom. So that means what's the top temperature? What's the bottom temperature? How do we do that? So now we got the top temperature, right? And sorry, top composition, distillate composition. And we also got the bottom composition. So if we have the top composition and bottom composition, how do we find the temperature of top and bottom? What kind of calculations should we do to find the top temperature and bottom temperature? So you can probably take a minute to think about it. What kind of calculations should we do to find the top temperature and the bottom temperature? Use bubble point of composition for top or bottom, the bubble point. You're right, it's bubble point, but it's top or bottom. Yes, bottom, because at the bottom, the product is leaving as liquid. But at the top temperature actually refers to the composition before it reaches the condenser. So that means it's entering the condenser as vapor, which means to find the top temperature, we need to do a dew point calculation, just like how we did last week. And to find the bottom temperature, we need to do a bubble point calculation. Okay, so since we already have done that last week, so I'm not really repeating every single step. So what we do here is to find the top temperature. Remember, to do the dew point, the way we do is we need to assume a temperature. So here, I just assume that the top temperature is 67 degrees Celsius. Okay, so we have 4 components. The distillate composition, we just estimated the distillate composition like this. Now, to do the dew point calculation, what I need to do is I need to assume a temperature because the pressure is already given for this problem, right? The pressure is given as 405 kPa. So we assume the temperature to be 67. So at the assumed temperature and pressure, I get the K values of all the 4 components. Now, remember, the distillate means before you condense it, it's entering the form of vapor, which means this composition actually refers to the vapor composition that enter the condenser. Okay. See, if in the distillation column, right? So the composition that we are referring to here, the XID, is basically this composition. And once it reaches the condenser, you condense it and collect your distillate here, right? So the condenser does not really change the composition. All the condenser does is once you reach the desired composition, right, it just condenses everything into liquid. But before it enters the condenser, it's entering in the form of vapor. So that means the distillate composition actually refers to the vapor composition. Now, to check whether this temperature is really 67, what you do is we get the K values at 67 degrees Celsius and 405 kPa from the deep pre-stir charge, and we note it down here. Now, since this is the vapor composition, the equilibrium liquid composition is estimated as xid over K, right? Remember, y equals kx, right? So this is what we did last time. So even though I wrote xid here, it actually refers to the vapor, which means it's y. Now, since y equals kx, x is y over k, right? Now, since this is y, to get the equilibrium liquid composition, we need to divide y with k. So we do that for all the 4 components. Now, to check whether the assumed temperature is correct, what you do is we check whether the sum of mole fraction is summing to 1, right? So when I sum all these things, I get it to be around 1.01, right? So when I add all this, I get it to be 1.01, which means my assumption is almost correct. So I can say that the top temperature is actually 67 degrees Celsius. Okay. Now, in the next step, what we do is we need to find the bottom temperature. So for that, again, I make an assumption that the bottom temperature is 132 degrees Celsius. Now, here I have 4 components again. So here is the bottom composition that we estimated in the previous stage, right? So this is the bottom composition. Now, just like the previous case, I take the K values at the assumed temperature. Now, at the distillation column bottom, this product is entering as liquid, or the product is collected as liquid, right? So this bottom product is collected as liquid. So that means this composition actually refers to the liquid composition. So to find whether the assumed temperature is correct, what we check is whether the corresponding vapor composition is summing up to 1. Actually, it should not be yi. Sorry, xi. It should be yi, right? So this yi is kixi, right? So xi means it's the bottom composition. Ki means the value of k obtained at the assumed temperature. So I get the k values of all these components at the assumed temperature. Then the vapor composition can be estimated by multiplying k with x. So I get these values, and when I sum everything, this again. When I sum all these 3, it's coming out to be around 1.01, which means the bottom temperature is actually 132 degrees Celsius. Okay. So when I did that, I get the K values of all the components at the top, and I also got the K values of all the components at the bottom. So in order to do the next stage, we want to find the relative volatilities. So the relative volatility means how volatile one component with respect to the other. In our case, we are trying to keep most of the B at the top, most of the C at the bottom. What it means is, what really matters is how volatile B with respect to C, which means we want to see the relative volatility between B and C, right? So we want C at the bottom, B at the top. So what we are concerned is how volatile B with respect to C. So because of that, we need to find the relative volatility of B with respect to C, okay? So of course, we can use any component as the reference component, but in this case, since our target is to keep C at the bottom and B at the top, we are more interested to see how volatile B with respect to C. So which means we need to estimate the relative volatility of B with respect to C. So can you find the relative volatility of B with respect to C at the top and also at the bottom in maybe 2 minutes? So here, what we are trying to do is we have the K values of all the components at the top, K values of all the components at the bottom. And our real concern is to keep B at the top and C at the bottom, which means we want to see how volatile B with respect to C. So based on the given information, what's the relative volatility of B with respect to C at the distillate, and what's the relative volatility of B with respect to C at the bottom? So can you find that? The relative volatility means it's the ratio of K values, right? Because K value indicates the tendency to go to vapor. Right. The K value is the tendency of a certain component to go to the vapor. But in order for one thing to go to the top and the other thing to go to the bottom, their K values should be different, right? So the relative volatility is the ratio of K values. So what do you think is the relative volatility between A and B? Not A and B, B and C. What's the relative volatility between B and C at the top and also at the bottom? Top 0.252. Okay, let me do the one for the. So here, what I want is I want to see how volatile B with respect to C, right? So that means the alpha between B and C is, so B's K value is 0.64, right? And C's K value is 0.26. So it should be somewhere around 2.26, right? So based on this, so this is the relative volatility between B and C at the distillate. Now I can also see how volatile each other component with respect to C. So since C is the reference, it's 1. Now, since A is lighter than B, right, this value is coming out to be 6.67. And since D is heavier than C, that value is less than 1. So based on this logic, can you find the relative volatility between B and C and also the other components at the bottom? The same calculations at the bottom. The reason these values may be different at top and bottom is because the top and bottom temperatures are different. Since the temperatures are different, K values are different. So even though when the K value of one thing change, the K value of the other thing also change, but then it may not change exactly the same way everywhere, right? So what I want you to do is find the relative volatility at the bottom, just like how we estimated the relative volatility at the top. Exactly the same calculation. So whatever I did for the top, just do it for the bottom here. So these are the K values at the bottom, right? So if C is the reference component, what's the relative volatility of B with respect to C at the bottom? Here, right, B and C. What is that? Exactly the same logic. We want to see how volatile B with respect to C at the bottom. Yes, somewhere around that. So all we have to do is just divide all those K values with the K value of C. So the one that we are really interested is how volatile B with respect to C. I think the difference may be a little bit on the rounding off. So if you get 2.05, that I'm pretty sure you did the right calculation. So now I got two values of alpha at the top and bottom. Okay. So we also solved the part B of this problem. We estimated the top temperature and we also estimated the bottom temperature. Now, the last question here is, what should be the minimum number of stages that we need to get this separation done? So if you keep the column under total reflex, so what should be the minimum number of stages? So for that, we need to apply the Fensky equation. So this is the Fensky equation. Now, we have the compositions of the distillate and bottom, right here. So from this table, can you predict what are those terms used in Fensky equation? So let me So this is the equation. So let me copy this equation here. So let me discard the other things, or probably put it in a new slide. So this is the Fensky equation. And I also have the compositions. Agree? Now, here I also found the alpha values. Agree? Now, in order for us to find the minimum number of stages, in order for us to find this, we need to know XLK at the distillate, XHK at the distillate, XHK at the bottom, XLK at the bottom, alpha light key, average, alpha heavy key, average. So we need to find 1, 2, 3, 4, 5, 6, 6 things, right? So we all know that B is the light key, and C is the heavy key. So what's mole fraction of light key at the distillate? Based on this table, what's the mole fraction of light key at the distillate? You can type it there. So based on this table, what's the mole fraction of light key at the distillate? See, distillate composition is here. Bottom composition is here, right? So from this, what's the mole fraction of light key at the distillate? Come on fast. Mole fraction of light key at the distillate based on this table. See, light key is B, mole fraction is here. And this is the distillate mole fraction, this is the bottom mole fraction. So what is the mole fraction of light key at the distillate? Is that question unclear? See, in order for us to solve this equation, we need to know the mole fraction of light key at the distillate, mole fraction of heavy key at the distillate, mole fraction of heavy key at the bottom, mole fraction of light key at the bottom, right? And the alpha values average. So the first one is mole fraction of light key at the distillate. So the light key is B, heavy key is C. So what's the mole fraction of B at the distillate? Right. LK at the feed 0.5, 0.62, bottom is 0.03. Right. So that means mole fraction of light key at the distillate is 0.62. Yeah, correct. So mole fraction of light key at the distillate is, no, not 0.62, right? Light key is B. So mole fraction of light key at the distillate is 0.35, right? The mole fraction of light key at the distillate is 0.35, right? Because this is the distillate mole fraction. Light key is B. So mole fraction of light key at the distillate is 0.35. And mole fraction of heavy key, then what's next? Mole fraction of heavy key at the distillate is, so this mole fraction of heavy key at the distillate is 0.03. Now, what's mole fraction of heavy key at the bottom? Heavy key is C. Mole fraction of heavy key at the bottom. How much is that? See, heavy key is C. What's the mole fraction of C at the bottom? See, this is bottom, right? So this should be the mole fraction of heavy key at the bottom. Now, the other one we need is mole fraction of light key at the bottom. So this is light key. Light key at the bottom is 0.07. So we got everything. Now, we need two alpha values. So alpha of light key. So there are two alpha values. So see, this is the alpha of B when we estimated from the top. This is the alpha of B when we estimated from the bottom. So we need to take the geometric average. Now, since the alpha of heavy key is 1, then of course the average is also 1. Agree? So when we apply these things, so we can see that the mole fraction of light key at the distillate is 0.35, right? Heavy key at the distillate is 0.03. Light key at the bottom is 0.07. Heavy key at the bottom is 0.51. Now, we have two alpha values. One is 2.46 and the other one is 2.03, right? So if you take the average, it's 2.23. So if you substitute, and of course, HK should be 1 because it has the same value at the top and bottom. So when you substitute these values, you should be getting the minimum number of stages to be 5.47. So what it means is, if we use infinite reflex in order to get the desired composition, that means these compositions at the top and bottom, there should be 5.47 number of stages. Now, there is one more thing we need to keep in mind. In a distillation column, there are a few stages, and we provide the heating at the reboiler. And finally, the top product is condensed at the condenser. Okay. So what happens in the condenser is, the product already reached at the desired composition when it enters the condenser. So all this condenser does is, it just cool it so that whatever enter here in the vapor form, it just condensed into liquid. So this condenser, it does not really change any composition. Whatever enter the condenser as vapor, it just condensed that into liquid with exactly the same composition. So the condenser, provided this is a total condenser, so if you use a total condenser, that does not really change the composition of the mixture that enter the condenser. So the condenser is not really considered as an equilibrium stage in a distillation calculation. But what happens at the reboiler is, whatever composition in the last plate, it enters the reboiler, and at the reboiler, you are providing heat. So when you provide heat at the reboiler, whatever enter reboiler, it enters at a higher temperature. So at that temperature, some of the things that enter the reboiler, it vaporize and go back to the column. It will not be collected because you are providing heat at the reboiler. So at the temperature that you provide at the reboiler, things get heated up, and the things that get heated up, it goes back into the column. But whatever still remain as the in the liquid form at the reboiler, that's the one you actually collect at the bottom. So what it means is, the reboiler is kept at a different temperature than any of these plates. So the reboiler also acts as one stage in a distillation column. Agree? If that's the case, if we estimate 5.47 theoretical stages in a distillation column, what it means is, we need 4.47 stages and one reboiler, because reboiler is also considered as one stage. Agree? Any question on this, or any question on anything that we discussed so far? Questions? All right, so I believe that part is clear. So the reason we consider reboiler as an equilibrium stage is because in reboiler, based on that temperature, the composition actually change. So that means the composition that enter the reboiler is not the same as it leave. Whereas a condenser is not considered as an equilibrium stage, because by the time it reaches the condenser, it already reached the desired composition. And all we do in the condenser is, we just chill it so that whatever enter as vapor, it become liquid. So there is no change to the composition. Whereas reboiler, there is a change in composition. And because of that, the reboiler is considered as a theoretical stage in a distillation column. Now, before I stop today, there is one question from my side, and you answer and we'll be done. Okay. So the question is like this. So here I estimated the number of stages to be 5.47, which means 4.47 trays and reboiler. Now, this 4.47 is trays, but we cannot put 4.47 trays, right? We can either put 4 trays or we can put 5 trays. Agree? Because we cannot put a half tray, right? So it should be a tray means you cannot have a fraction. So in this case, what's the minimum number of stages? The minimum number of stages, is that 4 or 5 or 4.47 itself? What do you think? And what's the reason for that? You answer and we are done. My question is clear, right? Because based on the calculation, I need 4.47 trays, but we cannot, or at least we think we cannot put a fraction of a tray. Agree? So you either put 4 trays or 5 trays. So is the minimum number of trays, should we consider that as 4 or 4.47 or 5? What do you think? We got about 2 minutes, so can you answer that part? So based on my calculation, I got 4.47. Should I use 4 trays or 5 trays or 4.4 trays? 4.47 trays. All right, remember when we actually do the distillation calculations, we cannot put half trays. But remember, this calculation that we performed is not to find the actual number of trays in a column. We are only trying to find, it's generally better to use 5 trays and a reboiler. Yeah, so it would have been correct if we are actually finding the real number of stages. But, so the one answer I got here is, it's better to use 5 trays. It would have been correct if you are actually finding the real number of trays. But what's happening here is we are only finding a theoretical number, because we are not going to run this column with minimum number of stages. Because if you want to run at minimum number, we need to use full reflex. But we don't run the column with full reflex, because if you do that, you cannot get any product, right? So the only purpose of doing this calculation is only to find a theoretical limit. So that 4.47 is just a theoretical limit. Okay. So that number you should not round up or round down. Okay. So we need to keep that number as it is without rounding. Okay. Now, later when we find the actual number of stages, of course, that number we need to round up, but round up or round down. But here, there is no rounding up or no rounding down, because this is just a theoretical number. So what we do in the next week's classes, we will use this concept to find the actual number of stages we will be putting inside a distillation column. So before I stop, is there any question, any part that's not clear? All right, so there is one question. So the question is, my question is, what are the limitations of using total reflex in distillation, and what are the challenges of designing a distillation column using total reflex in designing? Because as far as I know, using total condenser, yeah, the difficulty with using total reflex means feed is entering, but you're not collecting anything. Whatever you distilled, you're just sending it back to the distillation column, which means you don't get any product. The purpose of doing distillation column is you want to get the product, right? So when you use total reflex, even though the purity may be achieved at the top of the column, you're not getting it. It's just sent back to the column. Agree? So in order to get the product out, we need some of the product to be coming out, right? So if some product is coming out, it's not total reflex. So the total reflex, we only do the calculation, and the only purpose of doing that is to get a limit on the number of stages. Okay. All right. So any other question before we stop? If there is no question, I think we can end the class for today, and we'll continue and finish this chapter next week. Hanif, in that case, over to you.
Okay, thank you, Professor Nisan, for today's lecture on multi-state separation. We truly appreciate your time and the effort you put into making this session as informative and engaging as possible. We are looking forward to the next week session. Oke, terima kasih juga untuk semua mahasiswa yang mengikuti perkuliahan hari ini. Saya harap untuk lebih aktif lagi, karena kan perkuliahan ini kita pantau ya, dan akan saya beri nilai untuk keaktifannya, dan juga saya sudah berkoordinasi untuk rombel B yang diampu oleh Prof. Ratna Dewi. Ini akan saya data semua. Oke, I think that's enough for today. Thank you again, Professor Nisan, and all the students for your participation today. Have a great day. See you next week.
See you. In that case, I'll see you all next week. Bye-bye.
Bye. Thank you, Prof.
Thank you, sir.
Thank you, sir. Yeah. Thank you, bro.
Have a good one.